torque on a bar magnet when placed in a uniform magnetic field. To find the torque, we consider a bar magnet like this, which is placed in a uniform magnetic field. This is my south pole and that is my north pole of the bar magnet. Let us place this bar magnet in a uniform magnetic field, making an angle theta. This angle is theta, making an angle theta with the axis of this bar magnet. So at this time, what will happen is that there will be a force, magnetic force acting at south pole as well as the north pole, as similar to that electric dipole placed in a uniform electric field. So this is my north pole. So from north pole there will be a force like this force, and from south pole there will be a force in opposite. So you know this, if there was electric field like this, we had done this, and there was what? A electric dipole. So this was plus Q and this was minus Q. This was the force like this. Okay. Wow. This force was Q E, and this force is also equal to Q E. Okay, because force, electric force is charged into electric field. So this is plus Q and this is minus Q. We don't need to write that. Similar to this one, there will be a force, this force at north pole, which is equal to M into magnetic field B. Similar to this. This was charge, so Q, and there was electric field, so E. Similar to this force, we have to write M into B. This M is here, which is pole strength, and there is F due to south pole, which is equal to MB. Okay, this is my M, which is my pole strength of the bar magnet. So these two forces are in opposite direction at opposite line of action. Okay, so one force is going this side and another force is going this side. Hence the line of action is different, because if this force was this and if it was like this, then the line of action would be same and none of the force, the net force here, will be 0. But this force is like this. Okay, so this will go this side and this will come side. It will give me a torque. Okay, so the two magnetic forces, force south Fs and force north Fn, act opposite with each other. Act opposite with each other. Act opposite with each other with same magnitude. With the same magnitude. This force and this force have the same magnitude but opposite direction. The two magnetic forces Fn and Fs act opposite with each other with same magnitude at different line of action. This is the line of action and that is the line of action, different line of action. It is not like this. If it is this, then this is line of action, same. Different line of action. At different line of action, hence it forms a couple of force. It means they are opposite and line of action is different. Couple of force, thus it gives torque. Thus it gives a torque. Okay, so the torque tau is equal to force into perpendicular distance. So this is the definition of torque. So let us consider a perpendicular distance, this and this. So let me name this as A, B and C. Okay. So the perpendicular distance is my BC, and what is this angle? This angle is also theta, because this and this are parallel and this is same. If it is 30 degree, this is also 30 degree. This is also 30, this is also 30, and each side the angle is theta. So this is equal to, how much is the force? You can take this force also, you can take that force also. So this force, we know this MB into perpendicular distance is my BC. So let us find the BC now. Let us find the BC. Okay. So this is torque on. Okay. So BC. Okay. This is equation number 1. Okay. From the right angle triangle ACB. ACB, because at C the angle is 90 degrees. So you have to write like this. At right angle triangle, you cannot write ABC. If you write ABC, then it means that at B there is 90 degree right angle. But we have C here, so I have to write ACB. So then sin theta is equal to Sachin ko pad haraya. Okay, sin theta is equal to Sachin ko pad haraya, which is equal to, what is my perpendicular? So AC, this is 90 degree and this is theta. So this is my base, and if it is 90 degree, the opposite is my hypotenuse, and this will be my perpendicular. So perpendicular is my BC divided by hypotenuse is my AB. Okay, so this is sine of theta, which is equal to, I will bring this AB here, and this is sine of theta equal to BC, and I want to find BC. Okay, so what is AB? AB is the distance of the bar magnet, that is 2A. From this point to that point is 2A. So this is equal to 2A sine of theta is equal to BC. Okay. Now substituting the value of BC in equation 1, what we get? Okay. So this is continuation. This all should be below this one. Okay. Substituting the value of BC in equation 1, we get this tau is equal to M into B is there into, what is BC? It is 2A sine theta. Okay. So if it is done, then I will drop all this topic also. Then what I get? If you see here, there is M2A. What is that M2A? Okay, let me write. Tau is equal to M2A B sine theta. And we know that magnetic moment M is equal to M2A. Okay, so this tau or torque is equal to M2A is magnetic moment, MB sine of theta. So this is my, what is this? Is my the magnetic torque. This is magnetic torque, or you can also write, or you have since M equal to M2A. Okay, magnetic moment. Okay. If I write electric moment, then this will be Q2A. Okay, but this is magnetic moment. This torque can also be written in torque vector, magnetic moment vector into the vector. Since A cross of B vector is equal to AB sine theta, isn't it? This A is my M, this B is my B. So AB, I have got A B sine theta, which is equal to A cross of B, that is M cross of B. So this is the torque, magnetic torque. So what are the maximum and minimum conditions? Okay, so condition 1, let us find when theta is equal to 0 degree. Okay, when the theta is equal to 0 degree, so then sine 0 degree is equal to 0. So it's 0. Okay, sine theta is 0, this 0 is sine 0. Therefore, how much will be torque? Torque is equal to MB into 0. This will be MB into 0. So this is equal to 0. So this is torque. So condition 1, when the angle between magnetic moment M and the magnetic field B is 0 degree, then the torque is 0, that is minimum torque. Okay, this is also called as equilibrium. Equilibrium. Okay, equilibrium conditions. It means that, so we know that the magnetic moment, thus magnetic moment M vector is direction from north pole to south pole. It is going like this, and this is the magnetic field. Okay, so this is magnetic field and this is the direction of magnetic moment. Now when this bar magnet is coming like this, and if it is landing like this, then they are parallel. That time the angle is here 0 degree. For an example, if it is 90 degree, if you reduce it, reduce like this, reduce, you get this much like this, and reduce, make the parallel, then the theta will be 0. At this time there will be no torque. Okay, when the angle is 0 degree, the torque is 0, or the bar magnet is at equilibrium condition, or there is minimum condition. When the angle between magnetic moment M and B is theta, because this theta is angle. Please remember, this is angle between magnetic moment and magnetic field. So the next condition, let us do it here. Okay, so condition 2. Okay, this is condition 2. When theta is equal to 90 degree, then what will happen? The sine 90 degree is equal to 1. Okay, sine 90 degree is 1. Therefore, almost will be the torque. This torque is equal to MB sine theta is 1, or this one is equal to MB. So this is the torque. This is my torque, that is, this is maximum torque. Maximum torque. So condition for the maximum torque is that when the angle between magnetic moment and the magnetic field is 90 degrees. So this is magnetic field, this is magnetic moment. At this time, this is 90 degrees. If it is just like, if you rotate it like this and you make it 90 degrees, there will be maximum torque because of this. Or this is also called as highly unstable. Okay, this is highly unstable. One more thing I want to tell is, this is my bar magnet. This can also be called as torque on bar magnet or torque on the magnetic dipole. Okay, both are same. Magnetic dipole and the magnet are same. Thank you.